What is front-end and back-end in VLSI, analog versus digital VLSI, which role has highest demand? We'll cover all this in this video. If you love electronics and want to make a career in this field, make sure you subscribe this channel. Knowing about the field you want to make your career in is very, very important. Before you get into anything, you should know what the role is exactly about and what they do, the future growth it has, as this will be a major part of your life in the future. So watch this video till the end. What are the different domains in the semiconductor industry? In this single video, let's cover all the different domains in the VLSI industry, demand of these roles, how to decide which role to make a future in, real life applications, so all the electronic gadgets you see around, let's see who makes what and how the role contributes in making it. There are mainly three fields in VLSI: analog VLSI, digital VLSI and mixed signal design. Well, the main difference here lies between the signals you operate on. But before we get into analog and digital VLSI, let's understand the basics of signals. What are analog and digital signals? All the signals that exist in the nature are analog signals, like sound, whatever we speak, light, electricity flowing through wires are all continuous signals. That is, at any point in time, you have a value for the signal. And if you sample this signal, you have a digital signal. But if all the signals in nature are of analog type, why require digital signals at all? Well, there are two main reasons for that: noise and storage. Removing noise from all the analog signals will be very complex, but in digital, with simple error detections, you can remove noise off. You can very well process analog signals, but how will you store it? Our memories are designed to store zeros and ones. If you see this analog signal, there are so many voltage values it is taking. Like when it is dropping from 3 volts to 1 volt, it can take up to infinite values. 2.7, 2.6, 2.4, 2.88, etc. But how will you store this much of data? That is why we sample the signal. Say if you want to store 3 volts, 1 volts, 2 volts and 1.5 volts. So your sample signal, that is your digital signal, will look like this. So you basically have to represent 4 voltage values, which you can represent using 2 bits. 1 volt as 00, 1.5 volt as 01, 2 volts as 10 and 3 volts as 11. You can easily store this using 2 bits. We can go into more depth on these signals in some other video, but for now, we know the basics difference between an analog and a digital signal. Once we know this, everything becomes simple. In analog VLSI, you deal with circuits that operate and process continuous signals, that is your analog signal. And in your digital VLSI, you deal with circuits which operate on discrete signals like your 0 and 1, your digital signals. In mixed signal design, as the name suggests, you deal with both analog and digital signals. So what are some real life applications for these domains? Well, for digital VLSI, you'll be working on making powerful CPUs and GPUs or memories, as mainly these deals with zeros and ones. And in analog VLSI, you'll be working on circuits, processing sensor data, audio and video processing, RF circuits. Basically, you'll be working on signals that vary continuously with time. But in today's day, most of the design are not purely analog or 100% digital. Like say a CPU or a GPU, which is mostly digital, also has analog requirements like regulating the supply voltage to your system. You cannot simply supply from a battery. You have to regulate the input voltage. This is basically a power management system and it is pure analog, but it is interacting with a digital system. So again, if you are working on the analog part, you should know the knowledge of digital circuits as well. For mixed signal design, as you have both analog and digital signals involved, you will be working on converters like ADC, analog to digital converter, or DAC, digital to analog converter. Coming to the demand, see, VLSI is a booming field, so the demand for all these fields is very high. But the number of jobs and the opportunities in digital VLSI are way more than both analog and mixed signal design, at least in India. Okay, but what is front-end and back-end in VLSI? Let's take digital VLSI. As you know, the CPUs and GPUs makers are all digital companies. To understand front-end and back-end properly, let's take an example. Say a company has to make a processor mainly for gaming. So the gamers can play games like Far Cry, GTA 5, PUBG with all the best benchmarks and FPS. So the sales team of the company will come up with all these requirements to the architectural team. For easy understanding, let's take this interesting analogy. Front-end VLSI people are like the top order batsmen and back-end people are like the middle order batsmen or the finishers. Based on the market requirements from the sales team, like in our case, a good gaming processor and inputs like performance, power consumption and area, the architectural team comes up with an architecture. Front-end starts here. In front end, we have mainly RTL design and verification. And our openers, the RTL design team, designs this architecture in Verilog or System Verilog. They'll be usually given an architectural diagram or in a written format. Like the system should take this input and give out so and so output, and you as an RTL designer should design the system in a hardware description language like Verilog, VHDL or System Verilog. Also, C modeling is done for the architecture, which means that they also design the architecture in C programming along with the RTL code. Why C modeling? We'll see later. So once your RTL code for the given architecture is ready, 1 down, 2 down come in, the verification team. They verify this RTL design and find bugs in the design and make sure the design is bug free. So here, first they have to understand the architecture completely and know what is the expected output for a set of inputs. But how do you know the expected output? Well, that is where the C model code for the architecture comes in. The verification team verifies the output generated from the RTL code with the output from the C model and checks what is failing and what is passing. Basically, if the RTL code output matches the expected output, it is a pass, and if it does not, it is a fail. So with all the bugs in the RTL code, the verification team goes back to the RTL team saying ki bhai, this was expected but something else is happening and it's failing. So please fix it. Then the RTL team fixes the bugs in the design. Then come our middle order batsmen. First, the synthesis team. Backend starts here. The RTL code is just a software implementation, right? But this code has to be finally put as a hardware. Basically, we need to physically implement this hardware description code. So for this, each part of the Verilog code is mapped to its corresponding hardware. Like the case statement is mapped to a mux. So your case statement is your software code and the mux is what actually goes in as a hardware. That is why every RTL design engineer has to make sure to write a synthesizable RTL code. Meaning every part of the RTL code can be mapped to a hardware component. Once the hardware component of the corresponding Verilog code is ready, our finishers come in, the physical design engineers. They place and route the hardware on the chip for the best optimized performance, power and area. Also, along with all the inputs from the synthesis team, we have scan chain inputs from the DFT team that is designed for test. These scan chain flops are inserted in the design so that later the chip can be tested for any manufacturing defects. The physical design engineer comes up with the final layout. Later, you have checks like DRC, that is design rule check. These rules are basically based on the manufacturers because finally the layout will be put on the silicon by the manufacturer like TSMC. So they'll have certain checks like the spacing between two metal layers should be this much or the width should be this much. So physical verification engineer verifies all this and cleans the design of all the DRC violations or any shorts in the design. For checking shorts, LVS, that is layout versus schematic, is done. Schematic is the input you get before you start your physical design implementation, and this is compared with the final layout. All the connections should remain the same, right? So this is checked to see if there is any shorts in the design. Later, the clean layout file without any DRC violation or shorts is given to the manufacturer for fabrication of the chip. Once the chip is fabricated, validation engineers test it for any manufacturing defects. Once the chip is validated and looks fine, it goes for mass manufacturing, and in this way, our gaming processor is ready so that we can play PUBG, GTA 5 for the best possible FPS. All these roles have a great demand, but if I have to compare between front-end and back-end, the number of front-end jobs are more than the back-end, especially verification roles. But how to decide what interests you? So first, make sure you study basics like digital, analog, Verilog, CMOS circuits, network theory, computer architecture, and STA. Once you have finished them, then decide between front-end and back-end. If you like or are strong in Verilog, C programming, computer architecture, then front-end is for you. But if you think you're more strong in CMOS, STA related topics, then back-end is for you. So should we prepare either for front-end or back-end or for both? I'll say it's okay to choose between front-end and back-end. But if you choose front-end, prepare for both RTL design and design verification. Do more of Verilog coding, system Verilog and computer architecture. If backend interests you, then go through the whole backend flow and start studying each stage in detail. I'll make detailed videos on what to exactly study and roadmap for each of these domains. So make sure you subscribe and let me in the comments below if you have learned something new and what topics you need videos on. Also, don't forget to check out the Insta and Discord ChipCam community links in the description. Let's build a solid electronics community. See you in the next one.